Hey guys, welcome to the next video. This is going to be covering electrophilic aromatic substitution. So this has to do with adding different functional groups to benzene rings. Alright, so let's get started. So I drew this little schematic here of how a general electrophilic aromatic substitution works. Obviously, each reaction has its own specific reagents, but this is going to help us get started to see what it generally looks like, right? And hopefully make the mechanisms a little bit more understandable. So we're going to dissect this one at a time, and then we can move on to the reactions. So let's start over here. We have a benzene, and it's going to be attacking this electrophile. Now, benzene isn't that great of a nucleophile, so we need to have a pretty good electrophile, right? And so that's with this E with the positive charges. That's going to generally be the slow step of the reaction, right? Rate limiting. Now, what happens if you look at this little part right over here? Since one of the double bonds reaches out and grabs that E, right? Let me color code this. So I'm going to shade in purple that double bond that was grabbed, that grabbed that electrophile. That's going to be this bond over here. Now remember, there was a hydrogen here. All carbons of benzene, right? If there are no substituents, they all have a hydrogen on every carbon over here, like this. Okay? So that purple bond grabbed that electrophile, and it's going to create a carbocation on this carbon since there is a vacant spot over there. All I showed here is how we can resonate those bonds around, right? Those two remaining double bonds, we can resonate them around to move that positive charge. And the final part is going to be some base that's going to grab the hydrogen, and then this double bond right over here collapses down and restores the aromaticity, right? So you guys just learned aromaticity. This reaction is going to break it, right? Benzene is fully aromatic. It's losing that pi bond, and so it's going to have only 4 electrons in the pi system, right? But the fact that we restored the aromaticity in the end by collapsing this double bond down to form a new double bond helps keep the reaction alive, essentially. You can think about it, right? Because if we can't restore aromaticity, this isn't going to end so well, okay? And so that's usually the fast step. Acid-base reactions are usually the fast sort of reactions. So, and what you can see is that this little resonance complex sort of thing, right, is called you can either hear the term sigma complex or the uranium ion, right? Both the same thing. So now that we have that covered, we're going to go on to the first reaction that we can pretty much, we're going to group it as one thing, but we can do 2 different sort of things with it. Right? We can add 2 different kinds of groups using one sort of reaction. So the first one we're going to do is called a halogenation reaction, right? And we can add a bromine or a chlorine, all right, for halogenation. So how does this work? So we're going to start out with the benzene. All these reactions start out with benzene. And we're going to do the Br2, right? Now, we can't just put Br2 by itself, right? Remember that when we had something like this from Orgo 1, we did Br2, we would get something like this. Remember this that was a really bad ring. Anti-addition, right? But in this case, benzene is too stable to react. So Br2 by itself doesn't cut it. So what we're going to have to do is we have to pair this with a catalyst. Now, the catalyst used in these reactions is going to be called a Lewis acid catalyst. A Lewis acid is something that accepts a lone pair. It doesn't have to do anything with protons, right? Or like let's say hydroxide ion. It has to do with the flow of electrons. So Lewis acids accept electrons. In this case, we're going to use FeBr3. All right, so how does this work? So to show the full mechanism, we have to show what happens between these two things, because Br2, right, since we said benzene isn't that good of a nucleophile, it's too stable, we want to make Br2 more electrophilic than it already is. All right, so this is what's going to happen. Here's our Br2, and here's Fe Br3. Okay, all those bromines have 3 lone pairs. What happens is one of these bromines is going to attack that iron. It's going to lead to this intermediate. The iron now gets a negative charge. It has another bond. This bromine is going to have 2 lone pairs now. And because it has 2 lone pairs and 2 single bonds, it gets a positive charge. This bromine over here stays with its 3 lone pairs. So this is the important intermediate. This is the electrophilic intermediate, right? Now, why is it electrophilic? Imagine if I broke that bromine right here, positive charge, right? It doesn't like that positive charge, so it wants to, essentially get those electrons back. So imagine if we broke this bond to get it onto that bromine, and now this Br is going to have only 3 lone pairs, right? That's going to give it a positive charge, right? So that's really electrophilic. That bromine does not like that. So that's why this is going to be electrophilic, but in the mechanism, it's going to stay like this. We're not breaking that bromine apart. That's just to show how it's more electrophilic. All right. So now once we have this intermediate, what happens is our benzene can come into play. So you see here that the benzene doesn't take part in the first part of the reaction, which is the Br2 reacting with the catalyst. All right. So what's going to happen is the benzene double bond can now reach out, grab that bromine. It's going to get kicked out, and it's going to give us this now. We have the Br. Remember, we had a hydrogen right here, so that's still here. This double bond was just used. It's no longer there. It's attached to that bromine now, but the other 2 double bonds, nothing happened to them. And now, since we've used this double bond to reach out and grab a bromine, it disconnected from this carbon, giving it a positive charge. All right. Now remember, we can resonate that around using that whole uranium ion intermediate. Right. I could bring this over here. Giving us this intermediate. And then I could bring this guy down, giving this intermediate. All right. And you may think that there's no what does this matter? Why resonate around anyway? It's going to come into play when in the future, when we're talking about how we can do these reactions, but with substituents already on it. Right? So that'll come later. And then in the end, what happens is, remember, a base is going to have to deprotonate our hydrogen, right? We need to restore the aromaticity. That's the most important part. If we don't restore the aromaticity, this reaction isn't going to be favorable, I guess you can think about it. Right? And so we're just going to show this arrow drop down. You don't really need to show what deprotonates it. And now we have this new double bond there, the old double bonds. And the Br is now added on. All right? And so you can see that we did this. All right? If you want to, let's say, maybe do the, if you want to show the proper deprotonation, Well, what happened is the Br that was attached to FeBr3, right? Remember that iron cell is the negative charge, the Br is now neutral. It got its lone pairs. That'll grab the hydrogen, using this bond, right? So what we showed by using this bond is it's disconnecting and grabbing that H at the same time. So this is going to form HBr and regenerates our catalyst, FeBr3, so we don't need to keep adding it. Alright? And so that's the bromination mechanism. What about if we wanted to add the chlorination, right? It's going to be the same thing. Same exact mechanism. You'd write Cl2 over AlCl3, aluminum this time. Right, and we put a chlorine there, plus HCl plus AlCl3, and then to sum up the bromination, Br2 over FeBr3. Put the bromine plus HBr plus FeBr3. Alright? And that sums up the chlorination and the bromination reactions, and you guys can just think of them as essentially just one reaction. X2, like a halogen, chlorine or bromine, over AlCl3 or FeBr3, depending on which one you want to do. Alright, and don't get too caught up in the catalyst. Alright, and that's it for this video. In the next one, we're going to be going on to the next few reactions that we have for electrophilic aromatic substitution. So I'll see you guys in the next video.